Hi there. I'm sure you've seen this before. Maybe you had some bananas behind these glass cups and you could see some enlargement of the bananas in the portions of the cups. This can be explained scientifically using scientific principles which we're going to be looking at in this video. This is Z Online School. In this video, you and I are going to be looking at an introduction to refraction. We are going to do this in a systematic way. And by the end of this video, you should be able to know what refraction is, the laws of refraction, and you should also be able to understand what Snell's law is and the refractive index. We also have bonus tips at the end of this video, so make sure you watch this video till the end to get the maximum value out of it. Let's begin with refraction. What is refraction by definition? I hope you've seen the videos about reflection. Refraction is also involving light. This is a process where light bends after it has passed through medium of different densities. When you say medium, what are we talking about? We're just talking about substances. For example, light might pass through air and it might have a certain speed. When light passes through water, it will have a different speed. Each particular medium that is found on the earth has got different kinds of densities. And therefore, when light passes through those different materials, it will get affected. And that's what really we're going to be talking about, the process of light bending after it passes through many medium. Now, examples of refraction, as you saw, we have those at the start of this video, where we have those bananas. A common one is this one here, where you put an object in a cup and then it looks like it's broken. This is the bending of light. This can be explained scientifically. Very soon we'll see what causes everything to change. Another picture here shows us how refraction can be observed. Later in other videos, or later as you're at school, you find out that you even do an experiment for this example of refraction. You're going to draw this and see how everything will come to this exactly in the picture. Now let's look at the laws of refraction. Before we talk about the laws of refraction, it's very important that we get an idea of how refraction looks like. Here we're going to have this line to separate two medium, air and water, let's say. I'm sure you've looked at water in most of the pictures we've had. So yeah, let's use those two medium. Air is less dense than water. What we're going to notice is that our light will bend in a certain particular way depending on the densities of the medium that are involved in refraction. But like we had for reflection, we're going to have a normal. One thing that you must always remember is that if a light ray comes at an angle of the normal, which is 90 degrees, for any surface, when a light ray hits a surface at 90 degrees, it won't get refracted. Let's say we had a light ray that was coming through at an angle. This light ray will bend like this. We're going to have two angles that will be formed that are very important. But I think we can label our rays first so that we reduce on the confusion. The ray that is first getting into a medium is known as the incident ray. Then the ray that bends is known as the refracted ray. It's not very difficult if you've understood reflection of light. Now, when we're measuring the angles for refraction, we always start from the normal. So we measure an angle from the normal to a certain ray. And therefore, in this diagram, we're going to have two angles that are very key. The angle of incidence and the angle of refraction. They're going to be very helpful when we look at the Snell's law and the refractive index. Now, again, here we're going to see that they will be abbreviated like this, I and R. A great question that people might want to ask is, well, how do I differentiate since the same letters that are used for reflection are used for refraction? Well, this is where the diagrams come to play. When the diagram looks like this, as you can see, it's very different from reflection. For reflection, we had another ray coming in this fashion. For refraction, it's like this ray is passing through. If there was no refraction in this kind of example, this ray was just supposed to pass through straight. Now, because it's getting refracted, it bends. This is why we see the pencil looking like it's broken. The light rays that we see using our eyes are going to bend, and therefore our object will look like it's broken or it's bent. Now, let's look at the actual laws. Remember this diagram that's here always. It's parts, and sometimes the fact that there will be some medium here, there will be some air or some water, anything will be there. It's very important to note that the incident ray, the normal, and the refracted ray are on the same plane. If you want to know more about planes, you can even watch the video about the reflection. Now, when you talk about a plane, we're just talking about them being on the same axis or being able to be drawn on a piece of paper. The second law talks about the value of the sine I divided by sine r being a constant. What this means is that if we get sine of the angle of incidence and divide it by sine of the angle of refraction, we are going to get a certain number that will never change for those particular substances. Let's say we have air and water in this example. If light travels from air going into water and we use the sine of the angle of incidence divided by sine of the angle of refraction, the answer we're going to get will be constant as long as we're using air and water. If we were to change, let's say our light ray moved from air into glass, we expect that the answer or the constant that we're going to get is going to be different because the two kinds of substances we have gotten are different. Later in this video, I'm going to explain to you why this happens. But for now, let's get talking about Snell's law and the refractive index. What is Snell's law? Well, Snell's law is very similar with the second law of refraction. Do you remember we had sine I divided by sine r, right? Yes. If you read here, we've got this sentence here that is giving us the description of Snell's law. Snell's law is just like you're describing that expression we have. The sine of the angle of incidence divided by the sine of the angle of refraction is a constant for light passing through one medium into another. You can see it's not very difficult to remember it. If you can remember the second law of refraction, it's very easy to state Snell's law. However, it's very important to note that the constant value may change depending on the direction of light through the media. What this means is that we might have the same media, for example, air and water, like we had in the previous examples. If light is passing from air going into water, the constant value will be the same. However, the constant value might change if the light moves from water into air. There might be the two same medium, but because of the direction of light, our incident ray and our refracted ray are going to be different. And if you think with me, the angles are going to be kind of switched, and therefore it's very possible that our answers won't be the same. With that said and done, now let's look at the derived formula from the Snell's law. I'm sure if you are attentive, you already know that it's sine I over sine r. Now, we usually use this constant and refer to it as the refractive index. So whenever you hear the refractive index, you should at least remember this formula: sine I divided by sine r, where I is the angle of incidence and r is the angle of refraction. It's very simple. Another thing you must remember is that the refractive index can be equated to many things. Here we're going to equate the refractive index to speeds. In most instances, refraction takes place from the air and then into a certain medium. Let's say it's the water, like we've been using over and again. So we're going to have c, which is the speed of light, being divided by the speed of light in that or in a particular substance. For example, when light is moving from air into the water, Light will have a certain speed in air, which we know if you've been doing physics, 3.0 times 10 to the power 8 meters per second. Again, we're going to be using this letter-like symbol, which looks like N, and we have another formula for the refractive index. It's very important to note what these letters stand for. Another way in which the refractive index can be expressed is using depths. And when we talk about depths, we're talking about distances. I'm sure it won't really make sense if we just say refractive index and depths. But if I show you an example of what I mean, I'm sure you get a lot more understanding. To make this even more interesting, let me take you through the formula, then explain what everything means. When we're talking about the refractive index and depths, there are two kinds of depths that we talk about: the real depth and the apparent depth. Don't worry, I'll explain them right in this part of the video. When we get the real depth and divide it by the apparent depth, we are able to get the refractive index. Now, before we go any further, it's very important you understand what real depth and apparent depth are. To explain this, I'm going to use this simple illustration. Let's say we've got a fish in the sea. If we observe from above this pond, we'll be able to see the fish. Now, one thing you notice is that because light is traveling from different mediums, it's going to be traveling from this water into the air, and just like we already know, light will travel at different speeds in particular substances. So what's going to happen here is simple. When light from the sun gets into the water, the fish is going to reflect that light, and then it's going to reach our eye. And so we'll be able to see the object, the fish, which is in the water, because the fish is reflecting light from the sun. Obviously, there are some fish that produce their own light, but this kind of fish, I doubt. At the point where we have the water and air coming into contact, or simply at the surface of the water, we're going to have the bending of light. If we were to draw some normals here, it would make even much more sense. Now, this is the actual place where we're going to be seeing the fish. We won't be seeing the actual one here because those light rays have been refracted or have bended. And so if we draw some ray diagrams, we're going to kind of see an image that's not actually where it is. And as you can see in the diagram, we're making the lines that are producing those images dashed, because that's not the exact place where the fish is. It's actually below that point. Now, this is where the principle of real depths and apparent depths comes into play. The distance from the surface to the actual object is what we call the real depth. This is the exact place where the object is. Then that depth where we have the image being seen is what we call apparent depth. It's the object being seen at a different depth. Now, when we get these two depths or these two distances and work them out like this, we are going to have the refractive index. Now, it's very important that in this video you become able to work out the refractive index and all these things. It won't make much sense after you watch this video, you don't know how to work out some problems. So right now we're going to look at some examples. In our first example, we'll be looking at the first form of the refractive index, where we have sine of an angle being divided by sine of another angle. As you can see, the question is telling us that light enters water at an angle of incidence of 30 degrees. Simply, the angle of incidence is 30 and the angle of refraction is 22 degrees. We're asked to find the refractive index of water. This question is very simple if you know the formulas. Of the three formulas, we're going to be using the first one we looked at, the one that's directly linked to Snell's law. N is equal to sine I divided by sine R. We're going to replace I with 30, R with 22. I'm sure I don't need to really be slow because this is just a simple calculation. When you reach this point, I'm sure you need to use a calculator to work out this. It's physics and you'll be allowed to use one. One thing I would like you to do is use brackets for the denominator and the numerator. So I'm going to say sine 30 here, close my bracket. You can see my calculator automatically puts the angle in brackets, so I'll add another bracket for the first brackets I added, then use division, then do the same for the denominator. Going to get sine and then divide it by and multiply it by 22. I add another bracket and everything is now separate. As you can see from my answer, the refractive index is going to be 1.33. Two decimal places are going to be fine for this question. Mostly if you go and check the internet for the refractive index of water, you're going to find that it has got recurring threes. Therefore, refractive index like we have solved is 1.33. Here, when we're talking about the refractive index, you don't need to worry about the units. Like you saw, it is a constant. It's just a number without units. Now, sometimes this question might be made a bit tricky. It's not making it even difficult. It's just trying to see if you have understood how this formula works. You might be asked to find the angle of refraction. Let's say we were asked to find this 22 degrees. In the question, we're just given the refractive index and the angle of incidence. How could we find the angle of refraction? Well, it's simple. What you just do is make sin r the subject of the formula, and then you get this simple expression here. If you want to know how to do that, you can check out our videos about how you can change subjects of the formula. But it's kind of simple here. When we have things that are like this in an equation and we're asked to change the subject of the formula of a denominator, we just swap the denominator and the thing on our left side of the equal sign, and we are partially done. The next thing here to do is get rid of the sign, and so we're just going to remove the sign on our left side and add a sine inverse to the right part of our equation. Therefore, r is going to be sine inverse of sine I divided by the refractive index. And now we just have to plug in some numbers. If this question read light enters water at an angle of incidence of 30 degrees, given that water has the refractive index of 1.33, calculate the angle of refraction, we could just have gotten 30, placed it where there's I, the 1.33, placed it where we have the refractive index. And now, guess what will happen if we punch this into a calculator? We're going to have something very close to 22. Let's see if that works. Let's forget about this answer by just pressing on. Okay, so we're going to start with the things that are in the brackets first. I'm sure you've heard of board mass. Like we do in mathematics, we use board mass. We sort out what's in the brackets first. So sine 30, you can see the calculator there has added some brackets, so I'm going to close the brackets to just keep everything correct, then divide by 1.33. Okay, it's given me an answer which looks pretty good. Now I'm going to find sine inverse of this answer. How do I do that? Well, I hit shift on most calculators and hit the button sine. What happens is that my calculator is now going to bring sine inverse function, and therefore I'm just going to say answer because I was just from finding this expression on my calculator. You must always make sure that the answer that is being displayed on your calculator is the answer that you want to use. So I'm going to hit equals, and like you can see, my answer is 22.08, an answer which is very close to 22 degrees. Like, it's very difficult to calculate 0.1 degrees, so this angle we found is very good and accurate for our answer. Now let's try to do another example. In the second example, we're going to be using the second formula we looked at. Okay, now the question reads, if the refractive index of water is expressed as 4 divided by 3, what is the speed of light in water when we take the speed of light in air to be 300 million meters per second. This is the 3.0 times 10 to the power 8 I talked about earlier. This number can be converted to scientific notation, and that's how we get that other number I talked about. Okay, so I hope you can remember that we had this formula. Refractive index is equal to speed of light in air divided by speed of light in a medium. So what we do here is just make some subjects of the formula. We're going to make V the subject of the formula. And like I told you, if we want to make the subject of the formula of the denominator, it's not a very difficult thing. We just swap everything on our left side of the equal sign. If there's no fraction, we just get that refractive index and swap it with this V. Therefore, V is going to be C divided by the refractive index. If that's difficult, sometimes just make use of this triangle that can be used to make subjects of the formulas in a very quick way. What you do is just cover the quantity you want to make the subject of the formula, and then use the quantities that remain with the symbols that remain. With that said and done, what we're going to be doing is just dividing that 300 million by a 4 divided by 3. We can do that on your calculator, I guess. Make sure your zeros are 8, and then you can divide by this fraction. Since we have a fraction in our denominator, we make sure we put the 4 divided by 3 in brackets. Another way of doing this is just simply calculating 4 divided by 3 separately and then dividing the 300 million by that answer you find. We can do everything in one calculation and it gives us this answer. You can see this is 225 million. Therefore, the velocity of light in water is 225 million meters per second. And now let's look at the third example. Here we're going to be using depths. So we've got a liquid which is 25 centimeters deep, and we're asked to find the apparent depth of the liquid if it has the refractive index of 1.25. Like I already said, refractive index does not have any units. What we're going to be doing here is again making the denominator a subject of the formula. So we're going to just swap these two terms here. You can see there's no fraction on our left side of our equal sign, therefore we can just swap these. So the apparent depth should be real depth divided by the refractive index. If it's difficult again, you can use this simple triangle, cover AD and the multiplication sign, and then use what remains. So AD will be equal to RD divided by N. Now we can continue. So this is how we're going to work out. We're going to replace the values in their respective places. RD is the real depth. And how do we know it's the real depth? Well, the question says the liquid is 25 centimeters deep. Therefore, the real depth of this liquid that we're seeing from the top of the liquid to the base, the depth or the distance is 25 centimeters. So if you get confused about the depth, you can just simply plug in the 1.25 where it's supposed to be. I'm sure you can't get mistaken what refractive index is, and then put the 25 in the remaining place. Now we're going to calculate this on a calculator again. Just like we did previously, we're going to calculate it. It's a very simple thing. There are no special things to do. We hit equals and it gives us our answer. The answer is 20. This example is just like that observation you've made after you looked at a swimming pool. When you look at the floor of the swimming pool, it usually looks shallower than it actually is. Or in other terms, the floor of the swimming pool will look like it's not very deep because of refraction. It will be being seen at an apparent depth instead of the real depth. You have successfully reached the bonus tip section. In this video, I've got 2 tips for you. The first is about density and refraction. These 2 things have got a very direct relationship. The more dense a substance is, it means the more difficult light will be able to go through. So if you have a denser medium or a denser substance, it means light is going to struggle to go through. Just think of a wall. It's not very possible that light will be able to go through a wall because I think it's a very dense object. Now, if we start going away from such objects to objects that are less dense, for example, glass, and objects that are made to be able to let light pass through, it becomes even more tricky to think of how density affects refraction. Because for the wall, it's like common sense. You don't even have to be taught that light can pass through a wall. When it comes to these transparent objects or translucent objects, it becomes very important to understand that when a ray of light passes through a dense material or a denser substance, the ray of light is going to bend towards or closer than normal. This is because there is going to be more and more difficulty to pass through. Remember that if a ray of light passes through the path of the normal, nothing is going to happen to it. Therefore, when there's difficulty to pass, it's going to start coming closer to the normal. While when a ray of light passes through a less dense medium or a less dense material, it will be able to likely even move faster than it was moving. In later videos, you're going to see how this becomes very important. The second tip is about absolute refractive index. Whenever you see this term as you are studying about refraction, always remember that this is just simply referring to when we have an incident ray coming from a vacuum, or simply the refractive index when refraction happens in a vacuum. A vacuum is just a place where there's no air. One reason why I think it's called the absolute refractive index is because there is no interference. In the air, we find some particles that we can't see. There's some water vapor and all these small substances that might restrict or affect the speed of light. The third tip is about the Snell's law. Obviously, you've wondered how it all came to be known as the Snell's law. There's no relation between sine and Snell. It doesn't add up. Well, it's because this law was found by a scientist who had Snell in his name. Thanks for watching this video till the end. Make sure you check out the time code in the description below. Use the links that have been provided there, and always remember to comment below so that we can get to interact.